Our lesson here is on rationalizing the denominator. Now, two terms that we've got in the name of this lesson that are important. Rational or rationalizing is to make something rational. Recalling back to our very first lesson in this topic on surds, a rational number is something that can be written as a over b, where a and b are both whole numbers. Okay, so it might be a whole number like 10 over 2. Okay, it might be a terminating decimal like 2 over 5. It might be a recurring decimal like 2 over 3. But it can't be something like the two fractions I've got written here on the left, root 3 over 2 or root 2 over 3. Those are both examples of irrational numbers because they are never-ending decimals that have no recurrence or no pattern to them, okay? And it means we cannot write them in this form a over b where they're whole numbers. The second thing is that the denominator is the term on the bottom of our fraction. Now, the reason we do this process, we make the denominator rational, is so that we can manipulate fractions more easily. I can add and subtract them together. I cannot rationalize a number, okay? The number root 2 is irrational. I cannot rationalize it. These two fractions here, root 3 over 2 and root 2 over 3, I cannot make those rational. The whole number. I cannot make them whole numbers, okay? Because they're irrational numbers. I can't just change what they are. But what I can do here is start to add these two fractions together by making a common denominator, okay? So my common denominator is going to be 6. I'm going to multiply the left fraction by 3 over 3. So I'll have 3 root 3 over 6. The right fraction is going to get multiplied by 2. 2 root 2 over 6, and then I end up with 3 root 3 minus 2 root 2 over 6. Nothing I can do with that. I can't simplify it any further. Now that question is just an example of how we might apply surds, how we might use them a little bit differently. But that question would be made a whole lot more difficult if I did something like this. If I made it 2 over root 3 minus 3 over root 2. Now, all of a sudden, I'm going to have to try to make my denominators the same by including a surd in them, which means I'm going to have surds in the top, surds in the bottom, not particularly helpful. So what I need to do then is I need to make my denominators rational. And how we're going to do that is by multiplying them by themselves. Now, the ultimate goal here is not to change the value of a number. Okay, I said before, I can't rationalize root 2. Okay, what about I just square it? That's nice. But root 2 is not the same as 2. Okay, so my goal here is to make the denominator, the bottom of my fraction, a rational number without changing the value of the number itself. Okay, let's have a look at an example. We've got a fraction here, it's 4 over root 3. Now, the denominator is the irrational number. The numerator is already rational, but I want the denominator to be rational. So what I can do here, to try to make that denominator rational, I can multiply it by itself, okay? I'm going to multiply that by root 3, which is going to give me a denominator of just 3, exactly what I want. But I've got a problem. I've now multiplied my denominator by something. I hope you can see that to keep the numerator, to keep the value of this fraction the same, I need to multiply the numerator by the same thing. Okay, I multiply numerator and denominator by the same value, by root 3. So I'll end up with 4 root 3 over 3. Now, if you put that in your calculator, you'll get the same thing, okay? You put 4 over root 3 and 4 root 3 over 3 into your calculator, you will get the same thing. Now, let's have a look at another example. Something along the lines of 6 over root 2. I'm going to multiply by the denominator by root 2. I need to multiply by itself. And that means I have to multiply the numerator by root 2 as well. Okay, what I end up multiplying by here, it has to be the equivalent of 1. Root 3 over root 3, root 2 over root 2, they're the equivalent of 1, which means by multiplying my fraction by 1, it doesn't change its value. I just select how I get that 1 by using root 2 in the bottom and root 2 in the top, which gives me 6 root 2 over 2, or to simplify that, 3 root 2. Okay, so I've actually eliminated the fraction altogether there by making the denominator rational. Now, basically what we're going to do here is we're always going to multiply the denominator um, by the surd component of that denominator. So what I mean by that is if I've got something like this, 1 over 3 root 5, I could go and multiply by 3 root 5 over 3 root 5, but I don't need to. Okay, I can just multiply by root 5 over root 5, and you'll see what happens here. I multiply by root 5 because I want to get rid of that root 5 on the bottom. And then I multiply on the top because I want to make sure my value of my fraction hasn't changed. So I end up with 1 root 5, or just root 5 on the top, and 3 times root 5, which is 5. 3 times 5 being 15 on the bottom. Okay, now how I got this 15, just to be very clear, is 3 times root 5 times root 5. And the root 5 times root 5 just gives me plain old 5. That's how I get 5 times 3 is 15. Now, what I've achieved is I've got a rational denominator. If I'd gone ahead and multiplied by 3 root 5 up here, if I multiplied by 3 root 5 instead of just root 5, I would have ended up with 3 root 5 on 45, which would simplify down to root 5 on root 5. So I don't need to go ahead and do that. I can just multiply by root 5 over root 5. I said the last lesson when we did expansion techniques that we would end up doing something with what we call the conjugate that employs the difference of two squares approach. Now, if I have a look here, I've got something that is irrational in denominator, root 3 minus 1. Now, let's employ the same logic we just have here. If I go multiply this by root 3 over root 3, I end up with 3 root 3 on top over, I'm going to have to put some brackets around this, over root 3 times root 3 is 3 minus root 3. Okay, now we've got a problem because whilst if you put this in your calculator and this in your calculator, you get the same thing. So we mathematically haven't done anything wrong, but what we were asked to do is actually to rationalize the denominator, which we didn't do. Okay, we haven't made the denominator rational, we've just turned it into a different irrational denominator. So what we need to do, in fact, is utilize that difference of two squares. Okay, which, in fact, what we're going to multiply here, I've got 3 over root 3 minus 1. What I need to do, I need to multiply by the same terms, but with the opposite sign in between. Now, I'll show you what this is going to achieve in a second. And I multiplied the top by exactly the same thing, just to make sure again that all I'm multiplying by is 1. This expression here simplifies down to 1. Okay, I'm multiplying by 1. Now, what happens? On top, we're going to have 3 root 3 plus 3. On the bottom, though, what I'm going to have is when I expand this all out, I have root 3 times root 3 is 3. And then I've got 1 times root 3, which is just root 3, plus root 3. I end up with minus 1 times root 3, which is minus root 3. And minus 1 times positive 1 is negative 1. Now what happens, as a difference of two squares always does, these middle terms collapse because they're equal but opposite. So what I'm left with here is 3 root 3 plus 3 over 3 minus 1 is 2. I achieved my goal. My goal was to make the denominator rational. Okay, I can't make the numerator rational as well. I can't make the whole thing rational, but what I can do is make the denominator rational. So that when I go to try to add that to another fraction, for example, let's say I was subtracting a half from that. Well, then what I could do at the end is just say, well, I can just, they've now got the same denominator. And I could go 3 root 3 plus 3 minus 1 on top, because the denominators are already the same. Much simpler to operate with than trying to use root 3 minus 1 and 2 as my common denominators. Okay, so if I am going to have more than a single term in the denominator, I need to multiply by what we call the conjugate. Now, the conjugate is the same set of terms, but with the opposite sign in between. So if we're to think about what's the conjugate of root 3 plus 2, well, the conjugate of root 3 plus 2 would be root 3 minus 2. Okay, the conjugate of root 7 plus root 8. Okay, that will be root 7 minus root 8. It's the same two terms, the same pair of terms, but with the opposite sign in between. Let's have a look at one more example. An example here that's got a little bit more to it, not in that it's actually that much harder, but there's just more layers to it and more places we can make a mistake. So I've got a denominator that has two terms in it. So that means I'm going to need to multiply by the conjugate. Okay, the conjugate again is the same two terms, root 5 and root 3, but with the opposite sign in between, root 5 minus root 3. Now it is coincidence here that that is what my conjugate is, what the numerator already is. That doesn't actually help me simplify it at all. It just means I'm going to have to multiply it and be careful. Well, we'll end up with a perfect square on top, but still needs to be expanded. Okay, so I'm going to multiply by the conjugate. Okay, the conjugate is the same two terms with the opposite sign in between. When I expand this out, I'm going to start with my numerator. I've got a perfect square, which means I'll have root 5 all squared, which is 5. And I'm going to have root 5 multiplied by minus root 3, gives me minus root 15. Minus root 3 times minus root 5 gives me minus root 15 again, no coincidence. And minus root 3 times minus root 3 gives me positive root 3 all squared, which is 9. Sorry, root of 9, which is 3. All right, let's see what happens here in the denominator. I'm going to use that difference of squares approach where I've got root 5 times root 5 gives me 5, and root 3 times minus root 3 gives me minus 3, and the terms in between will be equal but opposite. So I'll end up with a plus root 15 and a minus root 15, which will collapse to give me 0, which is what I want, okay? This is my goal. This is my end game, to get the denominator rational. I've still got some terms I can simplify here, but I've got a rational denominator. We are good to go. Okay, so on top I've got 5 plus 3 is 8, minus 2 root 15 over 2. Now as a very last little step here, this is getting right up into the upper echelons of neatness and tidiness. Is what I can see is all my terms here share a common factor of 2. I can't go and do this. There's a 2 and a 2. I'll cross those out. No, I can't do that. Okay, I can't go and do that. I need to actually look for a common factor for all terms here. Now, what it means is I'm going to divide every term by 2. Okay, or actually, my real process is this. I'm going to take out the common factor of 2 on top to get 4 minus root 15 over 2, which simplifies to, well, the 2 and the 2 now can be crossed out. They can be divided out because they are a common factor to all terms. I get 4 minus root 15. Now, there's a little exercise here. Go and put that in your calculator, and that in your calculator. You'll see they are the same expression. They do have the same value, the same numerical value, just two very different representations of the exact same thing. Okay, so we started off by multiplying by the conjugate, which is the same two terms but with the opposite sign. A couple of expansions to deal with, and then simplifying with a common factor. I hope this has been helpful.